Okay, so we started out this process trying to find the area under the curve, and now we're moving on to section 5.5. We're going to go over a lot of notation and vocabulary, and this is going to be very important for Math 5B because we need to be able to go back and forth between the sums and the notation that we're about to go over. So we started out trying to find the area under the curve, and what we did in our previous sections is we made it nice and easy for us by making all the intervals of equal length and then finding our height of our rectangle by choosing some point in the interval, in each interval, to plug into the formula to get the height. But there's really no need to make all the intervals equal length. And so in this section, we're going to generalize that and have lengths, intervals of different width, of different length, okay? Like as we see in these two pictures. Okay, so we'll go over some vocabulary, right? So a partition of the interval AB is just a collection of points. X naught will be A, and then x1, and then x2, and then so on. And xn will be B. That divides the interval AB into n subintervals, of lengths. And now all the lengths are not the same. Delta x sub 1, the width of the first interval, is x1 minus x naught. Delta x sub 2 is x2 minus x1. It's always the right minus the left. Delta x sub 3 is x3 minus x2, and the width of the, and so on all the way until the nth interval, which is of length x sub n minus x sub n minus 1. And so here, we're just getting comfortable with that. It's the same thing. We're approximating the area under the curve. You can look at it that way. And all we're doing here, the only thing we're doing different here is all the intervals aren't of equal length. Okay, so this says find the value of the summation from k equals 1 to n of f of x of k star delta x of k times delta x of k, where your function is the cosine of x, the a is equal to 0, and the b is equal to 2 pi, and n is equal to 4. So all this is really, if we draw a picture, this will make it a lot clearer. So let's see what we're doing here. The cosine function is what we're working with. And the cosine function at 0 starts up at 1. And then at pi over 2 goes to 0. And then at pi it goes to negative 1. And then at 3 pi over 2 comes back to 0. And then at 2 pi comes back to 1. So this is a rough picture of what the cosine function looks like. X. This is y equals the cosine of x, y. And again, we're doing the same kind of thing we were doing last time, except that you're starting at 0. Your delta x sub 1, the width of your first interval, is pi over 2. So you are taking your first interval from 0 to pi over 2. At delta x sub 2 is 3 pi over 4. So then your second interval goes from pi over 2, and you add the 3 pi over 2, and a half plus 3/4 is 5/4. So 5 pi over 4. So that's pi and a quarter more will be 5 pi over 4. So your first interval goes from 0 to pi over 2. Your second interval goes from pi over 2 to 5 pi over 4 because the width was 3 pi over 4. Your third interval will go from 5 pi over 4, and again it's going to go up by another half, 2/4, so it's going to go to 9/4. 9/4 is going to be 9/4, Ooh, that's not 9/4. 9/4. 2 goes in, I'm sorry, 4 goes into 9. I'm sorry, 5/4. That's what I'm doing wrong. No, 5/4. And then 9/4. So the 5 pi over 4 plus the 2 pi over 4 plus the half is 7 pi over 4, which is 7/4 is a quarter away from 2. So that's your 7 pi over 4. And then finally, your last one is a width pi over 4, because then you have to get over here to 2 pi. And so your first interval goes from 0 to pi over 2. Your second interval goes from pi over 2 to 5 pi over 4. We were not given the endpoints, we were given the widths. So you can get there by just adding. And then you go from 5 pi over 4 to 7 pi over 4, and then from 7 pi over 4 to 2 pi. Okay. Now, in this first interval, you're going to put in pi over 4, which is right in the middle, into your formula to get the height. So the width is going to go all the way across, but the height comes from pi over 4. Now in your second interval, you're going to get this, so then the rectangle is this rectangle right here. In the second interval, your height is going to be gotten by putting in pi. And so at pi, it's -1. And so then you're going to go down to -1, go over here, down to -1, go over here, and then up. And this area right here, this will be a negative area because it's below the x-axis. In your third interval, I'm sorry, your second interval goes from pi over 2 all the way to 5 pi over 4. So this should be all the way over here. That's your second rectangle. In your third interval, you're going to put in 3 pi over 2, right? 3 pi over 2, that's this one right here. And that gives you a height of 0. And so your third rectangle is flat. And so that looks like that. And then for your fourth rectangle, you're going to use the left endpoint, come across, and you're going to find this area. And that's all they're asking you to do. The only difference between what we're doing right here and what we've done before is that the intervals aren't all of equal length. So then the summation from k equals 1 to 4 of the cosine of x sub k star times the delta x of k. What you're doing is you're just finding the area of each of these rectangles. So the width of the first interval is pi over 2. You're putting in pi over 4, which you get the square root of 2 over 2. For the second rectangle, your width is 3 pi over 4. The height you get by putting in the -1. For your third rectangle, you're putting in pi, which gives you a -1. And then for your third rectangle, you are the width is pi over 2. Right? So delta x sub 3 is pi over 2. But you are putting in the pi over 2. You are putting in the the 3 pi over 2. And so then that gives you a value of 0. So that goes away. And then plus the last interval has a width of pi over 4. delta x sub 4 is pi over 4. And the height you get by putting in 7 pi over 4, which is also the square root of 2 over 2. You can get a common denominator, write that all as one fraction. You can get a decimal approximation, whatever you want to do. It's the same thing we've been doing. We're approximating the area under the curve, but now we're allowing both positive and negative areas, and all our widths are not the same. So moving on. So if we go through and we find a Riemann sum, this is called the Riemann sum, and then take the limit as the width of the rectangles goes to 0. So if we form a Riemann sum, since the widths are not all the same size, what we're going to want to do is not necessarily have the oh, I'm sorry. Now that I'm looking at this, I realized I forgot something, right? So the max delta x of k, the largest width, since they're not all the same size, we can talk about which one is the biggest one. And we have a pi over 2, a 3 pi over 4, a pi over 2, and a pi over 4. So the answer to part B is that the biggest width is 3 pi over 4. Okay, so what we're doing different is we're allowing the widths to be of different size. That's what makes it a Riemann sum, a general Riemann sum. And so we're going to find the exact area, we're going to want to take a limit, but it's not going to be a limit as n goes off to infinity, because what we want is we want that biggest rectangle to keep getting smaller and smaller. So this is a different kind of limit. It's right here. It's the limit as the maximum delta x of k goes to 0, and then of this summation from k equals 1 to n. This limit may or may not exist, and so a function f is said to be integrable on the finite closed interval from a to b if this limit exists and does not depend on the choice of partitions or on the choice of the points x sub k star in the subintervals. When this is the case, we denote the limit by the symbol. This is read the definite integral from a to b of f of x dx. And so what this means, right, the meaning that this has is that this is the limit as the maximum delta x of k goes to 0 of the summation from k equals 1 to n of f of x of k star times delta x of k. This is just basically the area of each little rectangle, and this ensures that the width of your rectangles goes to 0, minimizing the error, right? Which is called the definite integral of f from a to b. We already talked about indefinite integrals. This is called the definite integral because the answer is going to be the area under the curve when the answer exists. The numbers a and b are called the lower limits of integration and the upper limit of integration respectively, and f of x is called the integrand. And so this is just going over notation and vocabulary so that we don't have to keep writing all of this. We'll just write it like this, but the two mean the exact same thing. And so then having gone over all the areas under the curves, you can then see that this is just the area under the curve. Use the given values of a and b to express the following limits as integrals. Do not evaluate the integrals. Well, we haven't gone over how to evaluate the integrals, right? So if we look back, what we were given is the right side of this equation. You have your delta x of k there, you have your f of x of k there, and then we're trying to go in this direction, write it as a definite integral. And so then you can see that the function that you're taking the f of x of k star of, you're putting the x of k star into the cube function. And so then that means then that f of x is x cubed, right? And so then this we would write as the definite integral from a is 1 to b is 2 of f of x, which is x cubed, and then the delta x we put in dx, right? And so that's how that looks. Now in Math 5b, we are going to start from these Riemann sums. We're going to start from these Riemann sums and then write them as definite integrals, because we're going to come up with an easy way of evaluating these definite integrals. That will come in the next section. For right now, we're just simply getting used to the notation. Okay, so this theorem should be of no surprise. If a function f is continuous on the interval ab, then f is integrable on ab, and the net signed area a between the graph of f and the interval ab is the definite integral from a to b of f of x dx, right? So that is what we were finding when we were finding the Riemann sums, and then we called the Riemann sums this thing, and so then that is the definite integral. What may not be obvious, not obvious to me, is that if a function is continuous, then it's integrable. Then that Riemann sum limit exists. But again, if it's continuous, remember what continuous meant. Continuous meant that you were able to get from f of a to f of b without picking up your pencil, which means you can't have any asymptotes or any or any breaks or any, like that. And so then if you're going to get from here to here in one curve, then it should be evident geometrically that the area underneath this curve is finite, and so that limit has to exist. Well, so you have that the limit exists and that it's equal to the area. That should be clear, because that's where we came up with that expression. Use definition 5.51 to express the integrals as limits of Riemann sums. Do not evaluate the integrals, right? And so then here, what you're trying to do here is you're trying to find the area from 1 to 2 under the curve of the square root of x. That's what you're trying to do geometrically. And so then this we found by taking the limit as the delta x max goes to 0 of the summation of f of x sub k star, summation from k equals 1 to n of f of x sub k star times delta x sub k. And that's it. Now, what's the usefulness of this? We're going to come up with a pretty easy way of doing this for functions that we can find the antiderivative of. But if you can't find the antiderivative of it, this expression right here is a good way to approximate it. Okay, and that's it. That's all you're being asked to do. Express the integrals as limits of Riemann sums. So you should try this next one on your own and not just watch me do this, because that's going to get pretty boring pretty fast. Okay, so, oh, I'm sorry, I didn't quite finish this. But the function that we're working with is the square root of x. So this is the limit as delta x max goes to 0 of the summation from k equals 1 to n of the square root of x sub k star. Times delta x sub k. And so then this next one is the same. This is your function. So this is then just the limit as delta x max goes to 0 of the summation from k equals 1 to n of your function that you're going to put your x sub k star in is the 1 plus the cosine of x. So you get 1 plus the cosine of x sub k star dx. I'm sorry, delta x. Okay. And you need to be able to go between the Riemann sums and the integral and the Riemann sums. It's going to be very important for Math 5b that you can go from the Riemann sums to the integral. Helps you set up the problem if you understand. All you're doing is calculating the area. Wrong way. Okay. Okay, so later we're going to come up with an analytic way of calculating these definite integrals. But for right now, if we look at them geometrically, and that is as the area under a curve, then we can do some of these without, we can do these geometrically instead of analytically. So this is sketch the region whose signed area is represented by the definite integral and evaluate the integral using an appropriate formula from geometry where needed. Okay, so again, geometrically, this is just asking us to find the area under the curve from the interval -10 to -5 for this function 6, and y or f of x equals 6 is the same thing as y equals 6, and that's just a horizontal line. And all we're trying to do is find the area under this curve over this interval. Well, that's just a rectangle, and so then the area is just the width, -5 minus -10, 5 times the height, and the height is 6. So that definite integral is 30. And there we go. Again, this is just asking us to find the area over the interval from -π/3 to π/3 for the sine function. The sine function starts at 0 and goes up, and then on the left side goes like that. And one of the things you learned about the sine function in trigonometry is that it's odd. That means that if I take this curve reflected here and then reflected across the x, across the y and then the x, the two pieces overlap. And what that means is that this area here is exactly the same as this area here. But the area on the left is below the x-axis, which makes it a negative area, and the negative on the right is a positive area, and they're exactly the same. So then in size, so one's positive, one's negative, so we get an answer of 0. Don't need to know how much each individual piece is. The whole thing is 0. So again, we're just trying to find the area under the curve. Now later we're going to come up with an analytic way of doing this problem, but it turns out that the geometric way is easier, right? So the geometric way for this particular problem is easier, not for all problems, but for this problem is easier. You should know what the graph of y equals the absolute value of x minus 2 is. That graph is an angle. When you put in 0, you get the absolute value of -2, which is 2. The vertex of the angle, it happens at whatever makes this 0. What makes that 0 is 2. And then once you get past 2, you go back up. You're trying to find the definite integral from 0 to 3. So then you're trying to find this area here, and you're trying to find this area here. Well, this is just the area of two triangles. And the formula for the area of a triangle is that the area of a triangle is 1/2 the base times the height. For this triangle here, the base is 2, and the height is from here all the way to here, which is also 2. Plus the area of this triangle, the base 1/2, the base is 1, distance from here to here is 1, and when you put in 3, you get your height of your triangle. 3 minus 2 is 1, the absolute value of 1 is 1. And so then you get 2, no, these go away, so you get 2 plus 1/2, 2.5, or 5/2. Now, you should be comfortable with what this graph is. If you're not sure, you can write it y equals the square root of 4 minus x squared. If you're not sure, you can square both sides and get y squared equals 4 minus x squared. If you're still not sure, you could add the x squared to both sides, get x squared plus y squared equals 4. You should be comfortable with the fact that that is a circle of radius 2. But with the positive square root here, your y value is always positive, so this is only the top half of the circle. So the graph is a circle centered at the origin of radius not 4, but 2. Right, so this here, so when you see x squared plus y squared equals r squared, the graph is a circle of radius r. So the 4 is 2 squared, so the radius is 2. So over here, -2, and over here is 2. And so then your graph is a half circle. And you're only trying to find the area from 0 to 2. So you're only finding the area of a quarter of the circle. So the area of a circle is pi r squared. So then you have pi, and your radius is 2, and it gets squared, but that's the whole circle, and you only have a quarter, so you need that quarter there, and so then you get pi. So the value of that is exactly pi. Now, again, later we're going to go over an analytic way of finding definite integrals, but in this class, we won't be able to do this problem analytically because we won't be able to find an antiderivative in this class. What we will be able to do is draw a picture and interpret the definite integral as the area under the curve and find the area under the curve. We'll be able to do the problem that way. Okay, some definitions. This first definition should be intuitive, right? If you're finding the definite integral from a to a, doesn't matter what the function is, that should be 0, right? So the area, if you start at a and end at a, should be 0. So that one's intuitive. This next one's a little odd. This is a definition. It's not a result. It's defined because we're going to want to do this from time to time, is reverse our limits of integration. And so we're going to define that to be the definite integral from a to b of f of x dx is the negative of the definite integral from a to b of f of x. So if you switch the limits of integration, you have to switch the sign of the integral. Not entirely intuitive, something you have to get comfortable with. This theorem should be intuitive based on the Riemann sums. If each, so if f and g are integrable on AB, and if c is a constant, then CF, f plus g, and f minus g are integrable on AB. And right, so if you were doing Riemann sums, and every term had a constant of c in it, then you can take that c and bring it out here and look at the limit then. And then the limit shouldn't change. It should just be c times the limit And so that's what this says. When you have a constant, you can take the constant out, but it needs to be a constant. It can't be a function of x. And the same way, if you had two integrable functions, that means that the limit exists, and you could break up your Riemann sums and take the limit separately, and then you'll get the limit of the sums. So when you have the definite integral of a sum of two functions, you can break it up as the definite integral of the first function plus the definite integral of the second function, provided both of those functions are integrable. Same thing with the difference. Those should be pretty intuitive based on our limit laws. Okay. This next one is fairly intuitive as long as you pick a c in the middle. So here's your the picture that makes it intuitive, but it works in any order. If f is integrable on a closed interval containing the 3 points a, b, and c, then the definite integral from a to b of f of x dx is equal to the definite integral from a to c of f of x dx plus the definite integral from c to b of f of x dx. And the thing here is that no matter how the points are ordered, right, they don't have to be in order. C doesn't have to be in between a and b. But when C is between A and B, that's fairly intuitive. If you're finding the area from A to B, you can just simply find the area from A to C, and add it with the area from C to D, and those two should be equal. That's the visual that you might have. So that's fairly intuitive, but what we're going to do from time to time is C may not be in order. C may be either over here or over here. It doesn't have to be in the middle there. Okay. So in this example, we want to find the definite integral from 1 to 4 of 3 times f of x minus g of x if we know the definite integral from 1 to 4 of f of x is 2 and the definite integral from 1 to 4 of g of x is 10. Okay, so again, just start with what we want to find, the definite integral from 1 to 4 of 3 times f of x minus g of x dx, and using the previous theorem then, since we know this one and this one, we can rewrite this as 3 times the definite integral from 1 to 4 of f of x dx minus the definite integral from 1 to 4 of g of x dx. This we know is 2. And this we know is 10. And so we get 6 minus 10, which is negative 4. So this new function, 3f of x minus g of x, has more area below the x-axis than above the x-axis. That's what this negative is telling you. Which kind of makes sense since the area above the x-axis was 2. When you multiply that by 3, you get 6. And subtract the 10, you get negative 4. Okay, so find the definite integral from 3 to negative 2 if the definite integral from negative 2 to 1 of f of x dx is 2, and the definite integral from 1 to 3 of f of x is negative 6. Well, so notice that these have the same endpoint here and here, and so then we can use our rule to take these two integrals and put them together. If the definite integral from negative 2 to 1 of f of x dx is 2, and the definite integral from 1 to 3 of f of x dx is negative 6, then the definite integral from negative 2 to 3 of f of x dx should be this area plus this area. which is negative 4. But that's the wrong order. So then we can now switch the order. So then the definite integral from 3 to negative 2 of f of x dx should be the opposite sign of this. And there you go. Use theorem 5.54 and appropriate formulas from geometry to evaluate the integral. Okay, so it is not obvious what the shape of 2 plus 9 minus x squared has, right? If you're not that comfortable with conics, that may not be that obvious. So what we can do is we can break this up as the definite integral from negative 3 to 0 of just 2 dx, and add it with the definite integral from negative 3 to 0 of the square root of 9 minus x squared dx. This one, you should recognize is just a horizontal line, y equals 2, and you're going from negative 3 to 0. And so then the width is 3, the height is 2, the area is 6. This one, 9 minus x squared, the square root of 9 minus x squared is a circle of radius 3. Centered at the origin. And we're finding this area here, a quarter of the area again. And so then this area is 1/4 pi r squared, and the radius is 3. So it's 9 pi over 4. And so then this is 6 plus 9 pi over 4. We have another theorem, fairly intuitive. If f is integrable on the closed interval from a to b, and f of x is positive for all x in ab, then the definite integral is positive. That should make sense. Your output's always bigger than 0, then your area under the curve is going to be positive. Next one, also fairly intuitive, right? If f and g are integrable on AB and f of x is greater than g of x for all x in AB, then the definite integral from a to b of f of x, the area under the curve of f, is more or equal to the area under the curve of g, right? So those two are fairly intuitive. And so use theorem 5.5.6 to determine whether the value of the integral is positive or negative, right? So you should see that this expression is always positive. And over the interval from negative 3 to 1, 3 minus a negative number is going to be a positive number. And so this expression here is always positive. So we can say x to the 4th over the square root of 3 minus x is bigger than 0 for x in the interval from negative 3 to 1, to negative 1, I'm sorry. Therefore, the definite integral, your output's always positive, so your definite integral is going to be positive, the area under your curve. Remember where that came from? It came from the Riemann sums. You were multiplying f of x times delta x and then adding those up. F of x is always positive, so each term will always be positive. When you add a bunch of positives, that should be positive. And so then that should be greater than 0. One of the reasons why knowing the Riemanns help. Right? So use theorem 5.5.6 to determine whether the value of the integral is positive or negative. Right? So the denominator is the absolute value of x plus 1. That's always positive. But now you're only using numbers in between -2 and 2. So the furthest to the right you go is 2, and 8 minus 9 is negative. In between, I'm sorry, at -2, you also get -8 minus 9. That's also negative. And so then you can see that this right here is always going to be negative. And so then a negative divided by a positive is going to be a negative. So then x cubed minus 9 over the absolute value of x plus 1 is less than 0 on the interval. Not always, but on the interval from -2 to 2. Therefore, your integral from -2 to 2 of x cubed minus 9 over the absolute value of x plus 1 dx is less than 0. And that is it. There's your homework for this section, section 5.5, 1 through 33 odd, and 39. This homework will be due next Thursday. Is that on the 30th of April? Okay.